Hi, in this video we are going to study the integration property of the Fourier transform. In other words, we are going to see how we can calculate the Fourier transform of the integral of a certain signal. So let us start with a signal x of t and its Fourier transform x of omega. The integration property is the following result. Then Fourier transform of the integral of x, the signal x, is equal to x of omega divided by j omega plus pi x of capital X evaluated at 0 delta of omega. Okay. Now we are going to see the proof of this result, but before that we know that differentiation and integration are operations which are inverses of each other. Now in differentiation, we know that differentiation in time domain corresponds to a multiplication by j omega in frequency domain. So we expect that in integration, since integration is the inverse operation of differentiation, and in differentiation we have multiplication by j omega. So in integration we will have division by j omega. But also we have this additional term, which is pi times the Fourier transform of x evaluated at 0 multiplied by the impulse. So where does this term come from? Okay, so we are going to see all these in the proof. The proof is as follows. First of all, integration by okay, let us define y of t as the integral of x. Now we claim that this integration operation corresponds to a convolution operation of x of t with u of t, where u of t is the unit step signal. Okay, why? Because y of t is equal to from minus infinity to plus infinity x of tau u of t minus tau integrated with respect to tau. Now this u of t minus tau is equal to 0 for tau greater than t. Because if tau is greater than t, then this argument, this term t minus tau, becomes a negative quantity, and the unit step function evaluated at a negative value is equal to 0. So since when tau is greater than t, this term is equal to 0, the upper limit can be replaced by t. And for such tau from minus infinity to t, t minus tau is positive, and therefore u of t minus tau is equal to 1. So here we have 1 as a multiplier. Therefore, Fourier transform of y of t, y of omega is equal to x of omega multiplied by u of omega, where u of omega is the Fourier transform of the unit step. So this is by the convolution property of the Fourier transform. Y of t is the convolution of x of t with u of t. Therefore, y of omega is equal to the product of the Fourier transforms, x of omega, u of omega. So x of omega is the multiplier. The Fourier transform of u of omega, the Fourier transform of u of t, which is u of omega, is 1 over j omega. We have calculated this in a different video. 1 over j omega plus pi delta of omega. Okay. Therefore, we have x of omega divided by j omega plus pi x of 0 delta of omega, because if we multiply x of omega with delta of omega is only non-zero for omega equal to 0. Therefore, we can here replace omega by 0. Okay, so this is the proof of the integration property. And in the integration property especially, it's important to understand how the second term containing the impulse comes into the picture, because at first sight one may think that differentiation in time domain corresponds to a multiplication by j omega in frequency domain. Therefore, integration will correspond to a division by j omega, but that is not correct. We have division by j omega, but we have this additional term coming from the unit step signal, because integration corresponds to a convolution operation of the signal with the unit step, as we have shown in the derivation. And therefore, by the convolution property, the Fourier transform of the integral of the signal is the product of the Fourier transform of the original signal and the Fourier transform of the unit step. And that's how we obtain this result. Now, we note the following as well. Note that x of omega is equal to, from minus infinity to plus infinity, x of t e to minus j omega t dt. This is the Fourier integral. And x of 0 is from minus infinity to plus infinity. So instead of omega, we are going to substitute 0. So we have x of t dt. Therefore, x of 0 is the integral of x of t over the entire real axis from minus infinity to plus infinity. So if this integral turns out to be equal to 0, the impulse, the term containing the impulse will disappear. And we will have x of omega divided by j omega as the result. But if the integral of x of t from minus infinity to plus infinity is not equal to 0, then we have this term containing the impulse. Okay, so we can now see an example. Okay, as an example, let us define the signal y of t as the integral of the rectangular pulse rect t. So we have this integral of the rectangular pulse. Remember, rect t is equal to 1 for t greater than minus 1 over 2 and 1 over 2. In between minus 1/2 and 1/2 we have 1 and 0 otherwise. And we know that rect t has the Fourier transform sinc omega over 2 pi. Okay, therefore by integration property, y of omega is 1 over j omega sinc omega over 2 pi plus pi. X of 0 is okay, so in fact we define rect t as our x, the signal x of t. So here we have x of tau integrated with respect to tau. Okay, x of 0 is equal to, so this is x of omega, this is x of t. So x of 0 is equal to 1. Okay, and we have delta of omega. So we only have a multiplication by 1. Okay, this 1 here is capital X evaluated at 0. The value of the sinc function at omega equal to 0. Okay. So this is the Fourier transform of y of t. But what is y of t explicitly? Okay, so we can have a look at this problem quickly. So now we have the rectangular pulse x of tau, which is equal to 1 in between minus 1/2 and 1/2. So when t is less than 1/2, y of t is equal to 0. Because we are integrating from minus infinity up to a value t which is less than minus 1/2, sorry, minus 1/2. So for that case, y of t will be equal to 0. So for t between minus 1/2 and 1/2, y of t will be equal to what? Okay, let us look at this problem. So we have, let me draw the figure once more. We have x of tau so this is minus 1/2 and this is 1/2, and t is here, for instance, in between minus 1/2 and 1/2. So we integrate from minus infinity to t. Therefore, the integral will be this shaded area. Okay? So y of t will be equal to t minus 1/2. It's the area of the rectangle. The height of the rectangle is equal to 1, and this length here is t minus 1/2. So we have t plus 1/2. And when t is greater than 1/2, what happens? Y of t is equal to 1. Why? Because t greater than 1/2 means we have the area of the rectangular pulse, which is equal to 1. So the signal y of t can be plotted as follows. Y of t, it is 0 up to minus 1/2. Then from minus 1/2 to 1/2, it increases linearly to 1, and then it is equal to 1. So this point here is 1, and this is 1/2. When t is equal to 0, the value of y of t is equal to 1/2. So y of t is this function. Okay, it is obvious that the impulse appearing in the expression of the Fourier transform is coming from this part of y of t, which extends from 1/2 to infinity as the constant 1. In fact, we observe that this is a shifted unit step. U of t minus 1/2. So in the Fourier transform of the unit step, we know that we have an impulse. Because u of t is not absolutely integrable, therefore its Fourier transform does not exist in the classical sense in terms of the Fourier integral. I mean, the Fourier integral is not convergent. So we observe that in y of t, in fact, we have such a signal. The unit step signal shifted by 1/2, this part of the signal. Starting from 1/2, we have the constant value at 1. So the impulse is coming from that part of the signal. Okay, thanks for watching.